Today's experimental mathematics speaker, joined with a defense, is Mr. Anthony Zaleski, hopefully in 49 minutes. Dr. Anthony Zaleski will speak about an experimental mathematics approach to some combinatorial problems. For those who don't usually come to this seminar, let me just remind you or tell you about the rule of seminar. Absolutely no texting, no electronic devices. And if you want to, if you need to text, you have to go out. But otherwise, no, thank you.
Okay. So yeah, first thanks to all of you for coming here, and I'd like to thank my committee also. So, like the title says, this thesis is all about using our experimental math methods to a bunch of different problems from combinatorics. So the way my thesis is organized is sort of like, there's a couple of kind of disjoint problems that I'm going to look at, and so it's going to be divided that way. So first, just a little overview. I'm going to start out with an introduction about like what I mean by experimental math, and then I'm going to do random walks, and then core partitions, which is like, I would say the bulk of my thesis is on that. And then I'm going to do a little bit with like using inclusion-exclusion methods on some existing problems. And then I'll finish with Boolean functions. Okay, so by experimental math, I'm assuming it's kind of clear already what we mean since this is the experimental math seminar. But basically we mean using computers to approach math problems, but a little more than just that, right? So a lot of people already do like numerics with computers and they solve PDEs and that kind of stuff. So we're more focused on like actually conjecture and theorems and proving theorems with a computer. So like a lot of what we do use is Maple, which it has symbolic capabilities, right? So it's all about using the computer not just as like a calculator, but more as an important tool in your proofs. And some methods we're going to use in this talk are using ansatzes. So basically, if you know your answer is going to look like a certain form, like maybe it's a polynomial or it satisfies some kind of recursion, you know that, and then you plug it into some kind of computer program, and you can teach the computer to learn that recursion or polynomial. We're also going to use a lot of generating functions, which I'll go over later, and dynamical programming. So basically that's like a way to implement, like say you have a recursion, right, like the Fibonacci numbers. So dynamical program is a way to implement that efficiently. And we're going to use a little bit of the online encyclopedia of integer sequences. So sometimes we have a sequence and then we'll look it up, and that will help us figure out more information about the sequence. And then just in this thesis, a big theme is going to be distributions of combinatorial statistics. So what I mean by that is we're going to have some kind of set of combinatorial objects. So like maybe random walks or core partitions. And we're going to ask, how are these distributed? So like, what is the average size of one of these partitions? Or what is the variance, and so on. Okay. So I'm going to start out with random walks. Okay, so the setup's pretty simple for the problem. Say we have a gambler, and he starts out with $0, and now he's going to start playing some games. And every time he plays, he's going to either win or lose $1, okay, with probability 1/2. Okay, and let's assume he quits after finitely many steps. Okay. So you probably heard of this problem. It's a pretty common problem. And so here's like a typical walk, right? The x-axis is time, and the y-axis is the amount of money he has at a certain time. Okay. And if I go too fast or you have questions, just stop me. Okay, so now what in his book on probability, Feller did is, for each of these walks, right, you can define a bunch of different statistics. So you give me a specific walk, well, you have the length of the walk is just the number of steps. And then you have these A1 through A4 are different statistics. So for example, A1 means the number of losing times, which is the number of points in time at which this guy had negative money. And then the number of break-even times is when he had 0 money. and so on. So you can define all these statistics corresponding to one of these random walks. And so the question we're going to think about now is, what are the distribution of these statistics? And also, yeah, so sometimes I'm going to sort of switch back and forth. A related problem is, instead of looking at a walk that like goes up and down, you look at a walk in 2 dimensions that goes either 1 unit to the right or one unit upwards, right? And in this case now, breaking even would correspond to being at a point on the diagonal y equals x, and losing would be like below y equals x. So you have this other way of looking at it. Okay, so before I go on to the case for walks, let me just review moments in general. Okay. So suppose I have a random variable. We have the kth moment is the expectation of the kth power of that random variable. So I'm assuming it's real value, right? So like the first moment would just be the expectation, or the mean of the random variable. Okay. And the kth central moment is just the expectation of the kth power of x minus its mean, right? So if you put k equals 2, you get the variance. And then there's the kth standardized moment, is I take the kth central moment and I standardize by dividing by the standard deviation to the kth power. Okay. Now, the sequence of standardized moments, so if you look at this sequence for different values of k, you can sort of think of it like a fingerprint for your distribution, right? So like the standard normal, well actually any normal distribution, if you look at its standardized moment sequence, you're going to get this sequence over here. So it alternates between zeros and the odd factorials. Okay. Okay, so like I said, the question in this thesis that we're going to look at a lot is, suppose you have a random variable that's like indexed, right? So like if you fix n, you can look at all the walks to the point n and comma n. And you have a random variable for each n, right? So our goal here is to, first of all, express the moments of the random variable in terms of n. And that will tell us something about its distribution. And then another thing we want to try out is, once we get that, look at what happens as n goes to infinity. So in other words, the asymptotic distribution, right? So maybe one question you could ask is it asymptotically normal? Because we know a lot of things like coin flips, right, tend to be asymptotically normal as n goes to infinity. Okay. Any questions at this point? Okay, so let's go back to walks. Or actually, wait, no, before that, so let's do generating functions. So now we're assuming x is a random variable, and the sample space is finite. Okay, so there's only finitely many outcomes, just like with our random walks, right? So if there's finitely many outcomes, you can define this generating function where you just sum over all the outcomes of t raised to your random variable. Okay, so t is just a formal variable, and so once you have this generating function, which will just be a finite polynomial in t, you can do some algebraic manipulations to get any moment you want. Okay, so the transformation you do is this. So if you think about that a little, it's pretty easy to see that. Basically, you just take your generating function, you apply the derivative, and then you multiply by t. You substitute in 1, and then you divide by the number of outcomes. And so you can get any moment that you want. Okay. So now that's our new goal. If we can find generating functions, then we can get the distribution. Okay, so we did this with the Feller stuff. So actually, Dr. Z already made like a maple package where he basically computed the generating function of all those statistics that I talked about before in like one big multivariable generating function. Okay, so he has a maple package that does that. And so we just sort of messed around with that package. And it's a little tricky, right? Because, so that package it's basically the sum of all the generating functions for all values of n. So it's not a finite polynomial. But if you look at a coefficient, it turns out to be a finite polynomial. So we had to do some like extra stuff using Maple's convert to formal power series function. But the point is, in the end, we were able to, in some of the cases, get the moments of those statistics that I talked about before in terms of n. Okay, so n is a symbolic variable. So let me show you an example. So these examples are going to be for the number of visits to the diagonal. Okay. So I'll just let you look at this a little bit. I mean, it's very complicated, right? This is just what Mabel spit out. But we got the mean, we got the variance, and I also didn't write it. We got some higher moments, and here are the limits of the standardized moments. So yeah, at this point, do you have any questions?
You know, what's the floating point of observation?
Yeah, that's a good question. I don't remember. Yeah, I don't remember what if you look at these as decimals, what they come out to be. And as far as I know, we didn't recognize this as some existing distribution. Yeah, obviously it's not normal, but I'm not sure what it is. So, okay, so now what if we get a little more complicated? So before we were looking at, you have two possible steps, right? You can walk to the right or you can walk up. So then we said, okay, what if you say allow arbitrary steps, right? So what if you fix some set of allowable steps, and then you look at the walks, say from 0, 0 to AB, that use only those steps. Okay. So now we want to see if we can do the same thing and figure out how the moments are going to behave. But since we can't really make use of the symmetries and stuff, in this case we're probably not going to get exact results like we did before, but maybe we can get some kind of numeric asymptotic estimates. And so that's what we did. And the way we did this is basically we said, okay, if you fix A and B, right, numeric, then the generating function is a finite polynomial. So we said, can we figure out a way to efficiently compute the generating function for fixed A and B, right? And the way we do that is with some dynamic programming. So we say any walk to AB is going to be a concatenation of some smaller walk plus the last step, which we know is some step in your step set, right? So you have you can express any walk as a concatenation of some walk plus the final step. And so this is what gives you your dynamic programming scheme for the generating functions. Basically, the picture I just showed you implies some type of recursion for the generating functions. Okay? And you need to keep track a little of how your statistics change and stuff, but it's doable. And okay, so now, and Maple has this thing where all you need to do is include option remember, and it automatically will make a little table, and it's going to store the previous results. So you don't have to it's not going to be exponential time because it stores the previous values of your function when you do your recursion. Okay, so this lets us generate data for a bunch of moments if we look at the walks from 0, 0 to n comma n. And so basically we just generated a lot of data, and then we tried to fit the asymptotics to, in this case it was a polynomial ansatz. Okay, so here's a sample table. So the statistic I'm talking about here is the number of times your walk goes below the diagonal. So for example, the first row is stuff we already talked about. So the first row of this table says if my steps are 0, 1, 0, 1, and 1, 0, then the expectation is n, okay? The variance is 0.3 n squared, so actually it's 1 over 3 n squared, but so this is obviously not exact. And then this is the limit of the third standardized moment, I think, and then this is the limit of the fourth. Okay. So yeah, our program, you can feed it any kind of steps that you want, and then it just makes a big table like this. So yeah, that's it for walks. Actually, no, one more thing. But are there any questions about that? Okay, so the one more thing I want to talk about is you can also define this in 3 dimensions, right? So you can let your steps be any steps in 3 dimensions. In this case, if you want to figure out, instead of the number of times it's below the diagonal, now we have the number of times it's in each of these 7 different regions. So it's a lot more work to keep track of. But we did make a function that does that, although we haven't really done much with it. Okay, so all this is in a Maple package that's on my website. Okay, so now, like I said, most of my thesis is on partitions. So I'm going to start with a definition of partition, which, like, hopefully a lot of you already know. So a partition of a natural number n is just a way to write it as a sum of smaller natural numbers. And the order doesn't matter, and you can have repetition. So in other words, we have a non-increasing sequence of natural numbers that sum to n. Okay? So n is the size of the partition. Each of the smaller parts are called parts. And so here's an example. 9 equals 4 plus 3 plus 1 plus 1 is a partition of size 9. Okay, and these have a lot of applications in other areas of math physics. So once you have your partition, 4, 3, 1, 1, for example, you can make your Young diagram, which says you just put in the ith row, or in the first row here, I'll put 4 boxes, and then the second row is 3 boxes, and so on. So your Young diagram is like a way to graphically represent a partition. And now, given your Young diagram, you can define hook lengths. So if you pick a box in your Young diagram, like this box right over here, the hook is just the boxes to the right, plus the boxes below, plus the boxes cell. So each cell is going to have its hook. And the hook length is just the number of boxes in the hook. So that cell will have hook length 4. Okay, so let me just fill in the rest of the hook lengths. Okay. So there's the hook lengths. And now this lets us define what I want to talk about in my thesis, which is core partitions. So an S-core partition means that your Young diagram avoids hook lengths of size S. Okay? So when you do your Young diagram, S does not appear as any of the hook lengths. And then an ST core means that neither S nor T appear as hook lengths. So sometimes call it a simultaneous core. Oh yeah, and so Dr. Stills actually pointed this out. Some people say divisible by S, but it turns out those are equivalent, so we don't have to worry about that. Okay, so like one of the first theorems about this, by Anderson, the number of ST core partitions could be infinite. Okay. In fact, it's only finite if S and T are relatively prime. Okay. And in that case, she found a formula for the number of ST core partitions. Okay. So if you look at the number of S plus 1 core partitions, where you plug in S plus 1 for T, it happens to be the Catalan numbers. So any questions about that?
Is that for any n?
Let's see. Where's n?
I don't know.
Oh yeah. So you're saying n is the size of the partition? Yeah, it can be anything, as long as they're ST core. Right. Okay. Okay. So now, sort of in the spirit of what we did with WOPs, we're more interested in not just enumerating these, but like the distribution of the size. So, in other words, if you look at all ST core partitions, assuming that S and T are relatively prime, you have some set of partitions that's finite. And you can define the random variable that's the size of one of those partitions. And so the question we're interested in is what is the distribution of that? So here's a conjecture that by Armstrong that was proved by Johnson about the average size of that random variable. So like I said, this is proved. And then later on, Dr. Z, he went further and he got up to the 6th moment of that random variable with Maple. Okay. So that's pretty much taken care of, right? And it turns out these moments are all polynomials. But now the question is, what if you require that they have distinct parts? Okay. So it turns out that actually changes things a lot. And in that case, what we have to do is sort of restrict to like even smaller families of partitions. So for example, S plus 1 core partitions. So if you look at S plus 1 cores with distinct parts, if you enumerate those, Stroud proved that it's a Fibonacci number. Okay. But as far as like the distribution of the size, that's where we did our work. So let's just, for easier notation, define P sub S to be the partitions we're interested in. And so now, just like before, we want a generating function, right? If we have a scheme to compute this quickly, then maybe we can look at the moments. Okay, so we need a fast way to compute that. So in this particular case, we got lucky. In Strauss' paper, where he proves that this number of these partitions is Fibonacci, he also gives a way to characterize them. So he says that a partition is an S+1 core with distinct parts, if and only if the perimeter is less than S and it has distinct parts. So by perimeter, I mean the size, the length of the largest hook. Okay. So if the largest hook length is less than S and the parts are distinct, that's what we're interested in. So this becomes now a question of counting these type of objects, which turns out to be easier. Well, it's not easier, but it's easier to look at it that way. So there are these things called Q binomial coefficients, right? And basically, a Q binomial coefficient is a polynomial analog of your ordinary binomial coefficient. And it basically computes the generating function of your partitions that fit in a certain box. So we were able to manipulate that a little bit and get this Q binomial sum that gives you the generating function for what I mentioned on the other slide. Okay. So we have the generating function as a Q binomial sum. And then after that, we use Dr. Z's package where you can just plug it, give it a Q binomial sum, and it will automatically figure out a recursion and prove that the recursion is true. So at this point, we have a fast recursive way to compute the generating function. Okay? And again, it's fast because we can do it dynamically where we keep on building up. Okay, so here's like a sample of some of our results. So basically we found that, so previously the moments were polynomials, right? But now when the parts are distinct, it turns out they're like polynomials, but then they involve some Fibonacci numbers. Okay? So they're still C-finite, meaning they satisfy like a constant coefficient recursion, but they're not polynomials anymore. So here's the expectation of the size of these partitions. And then we got up to moment 16. And in this case, if you take the limit of your standardized moments, they approach the sequence. So that's, I mean, it's very good evidence that this time the size is asymptotically normal. So if you add the restriction that the parts has to be distinct, all of a sudden it's asymptotically normal. Okay. Any questions about that? All right, so I have like more things to go over. So real quick, I want to just talk about some other partition stuff I did. So basically, you can try to do this generating function thing with other families of partitions, right? So the next easiest family where the GCD is equal to 1 is you look at successive odd integers, right? They're always going to be relatively prime. So if you look at 2s plus 1, 2s plus 3 cores with distinct parts. So in this case, we don't have that nice like perimeter characterization. So what we did here is we use a bijection that's, again, according to Anderson, where, first of all, you define this post set, okay? So I'm not going to go too much into this, but basically, given S and T, you can define a certain post set, and then the order ideals of this post set will correspond with the core partitions, okay? Where an order ideal is just something that's like closed under your relation. So if A is in my order ideal, then everything less than or equal to A is also in the order ideal. Okay. Yeah. So what we have to do is look at what does our post set look like for this family of partitions. Okay, so this is going back to the SS plus 1 case. This is an example of your post set, right? So the way we're drawing this post set is increasing is this way or this way, right? So like the biggest element is over here. And then the stuff that I marked in red is an example of an order ideal. Okay. Okay, so in this case, you can enumerate the order ideals by some kind of Catalan type of decomposition, right? You say, okay, an order ideal is like a concatenation of two smaller order ideals, and you can do the Catalan thing. But we already took care of this case before, so okay, before I go on, this is, so I said there's a bijection, right? If you have an order ideal, you get a partition. And this is how the correspondence works. So if my order ideal has these labels, what you do is you throw those labels in the left column of your Young diagram, and they become the hook lengths. So we have a bijection between order ideals and partitions. Okay. Any questions about that? So going back to this new case we're looking at, we made this program that can plot these posets. So in this case, here's a typical poset. So it's actually not exactly triangular, right? It's like the base, it has two levels to it, if you look closely. So now to enumerate the order ideals of this is a little trickier. You can still sort of do this decomposition, but you need to be more careful. Oh, and also let me go back. Because we want distinct parts, right? Another restriction is we want the labels in the order ideal to be non-consecutive. Because under this bijection, if you have consecutive labels, then you're going to get a repeated part. So that's another restriction in our order ideals. Yeah, so I'm not going to explain because it's very complicated, but it's not hard, it's just a lot of computation. But we came up with a recursive scheme. So basically we said any order ideal of this looks like some type of concatenation of smaller order ideals. And again, that gave us some type of recursion for the generating function. And then again, we computed a bunch of generating functions, and we got theorems like this. So now again, the average size of the polynomial, and again, we did the moments, and it's actually not asymptotically normal in this case. So any questions about that? Okay, and you can do this poset game for like other families of partitions, but it's basically the same thing. You plot your posets, and you look for some type of structure to them, to the order ideals, and then you make your generating functions. So in our thesis, we do S ds minus 1 cores, we do S plus 1 cores with parts repeated at most k times. We do into odd parts. And for the odd case, actually, this method was not working that well. It was very slow to compute. And then, so we put our paper on the archive, and we said, if someone can improve on it, we're going to donate $200. Well, Dr. Z is going to donate $200 to the OEIS. And then pretty quickly, Paul Johnson emailed us, and he solved it, and he gave us the proof. So we donated to the OEIS for him. Yeah. So that's it for partitions. Before I go on, are there any questions about that? Yeah.
Is there a reason to stop at 2?
Is there a reason?
2 simultaneous numbers should not appear sequence?
Yeah. So people definitely study like if there's more than 2, and I think that there's the same result where like then it's finite if and only if all the numbers are relatively prime, right? But I don't know anything about that, so. Okay, so now I'm just going to change gears. So this is sort of like, on the side we did this, it was a bit of a reach thing that we did, but we had this idea, right? So first of all, let me just review, inclusion, exclusion, right? It's if you have a bunch of probability events, and you want to figure out the probability of the union, then we have the inclusion-exclusion formula. So a lot of times, like, when you do the probabilistic method, right, you end up using this, but you only compute like the first term in the sum, right? So what I mean is, if you truncate inclusion-exclusion, then you get this upper bound, right? That the probability of the union is at most the sum of the probabilities. And just that bound can give you a lot of nice results, right? So like the lower bound for Ramsey numbers uses that, basically. So our idea is, what if we compute more terms in the inclusion-exclusion sum, okay? So the Bonferroni inequalities tell you if I compute some terms in the sum and then I truncate inclusion-exclusion, then I end up with like either upper or lower bound on the probability, depending on how many terms I go out. So our idea is maybe if we take this further, we can improve the existing bounds.